It shifted left, looks like 3. Nope, shifted left by 4 and it's up by 5. In fact, you can actually tell from this equation. Remember, this is at x minus h. So h is a 4, and this is your k out here. The k is a 5, so it's left 4, up 5. 4, up 5. So that's right here. This is negative 4, and this is 5 right there. And that's good enough. Okay, we can pick some other values, but if you go to your table here, second table, I can see when x is 0, out comes 7. Great, there's another point. The next good point is at 5. 1, 2, 3, 4, 5. It goes through 8. So there we go. There's 3 points, and there's what the graph looks like. Determine the minimum values for x and y. So x min would be negative 4. Y min, the lowest y value you can see is just 5. Okay, that's this point right here. That's the smallest y and x it goes to. 37 was the domain and range for the graph in 36. So domain looks like x has to be greater than or equal to negative 4. Range starts at 5 and goes up, so y is greater than or equal to 5. Using a function of the form 4 times b to the x power, give a value for b so that it's exponential growth. The key thing is, if b is greater than 1, you have growth. So for part A, if you want exponential growth, b would have to be anything greater than 1. So b could equal like 2. That give you growth. Exponential decay problems, that b is a fraction trapped between 0 and 1. And so we could say a, b equals something like a half. Okay, and you can actually see these. I'm going to show you one real quick here. I'll put a 4 times, and I'll use the 2 in my example A, and I'll raise it to the x power, and I'll hit zoom 6, and you'll see it grow really fast. So it's going bigger and bigger and bigger. And then I'll do an exponential decay one. So I'll do the same problem, but 4 times. And this time I'll put that half in there. Parentheses 1 divided by 2, and parentheses, there's my half to the x power. And I'll hit zoom 6 again. So you'll see the first one come in. There's our exponential growth. And then the other one, you'll see it decaying. As x gets bigger, it gets smaller. Evaluate the log base 32. Here's what this says, and I just talked about logarithms earlier in the video. You're looking for the exponent on this base. So you say 2 to what power gives me 1/32. Okay, and these are actually little number puzzles. So what you do is you work on this right-hand side, and hopefully you can get it to be a 2. It turns out 2 times 2 times 2, and I can show you on my calculator here. Oops, clear, second quit. 2 to the 5th power is a 32. And now I'm going to rewrite this whole thing as 2 to the x equals. I'm going to take this and use my negative exponents to write it so the base is 2. And I can compare it and see that the exponent is negative 5. So this is equal to negative 5. Now I'll show you how to do that one on your calculator here. Watch very closely. If I want the log base 2 of 1/32, here's what I enter into my calculator. I go log of 1/32. This is a log base 10, but we don't show the 10. Our calculators do log base 10s. And then you just have to divide it by the log of the actual original base. So here I go on my calculator. I'm going to go log, left-hand column, you'll see it about midway down, of 1/32. And I'll divide it by the log of 2. And that should give me what I have up there, negative 5. There we go. So our calculator can do that if you know how to enter it. Graph f of x equals 2 times 3 to the x power and show key features. I'm assuming that should be on my number graph up here. So I'm going to put it there. I'm not sure why it didn't print the way it's supposed to. Well, figure that out when I look at it tomorrow. So anyway, so I'm going to graph this function. This is that one we just looked at, except I had a 3 in there, or a 2 in there, and it was exponential growth. Well, this is a 3 in there. That's bigger than 1, so it's going to be exponential growth too. And I'll show you the key features they want. These things are a piece of cake. 2 times 3 in parentheses to the x power. So just like it is. Zoom 6 it. It's going to be that exponential growth thing. Okay, and you can generate things for this all day long, but one of the key features, if you notice, this thing goes through, has a y-intercept of just 2. And that's always this number that's out front. We'll tell you what the y-intercept is. So if we're graphing this thing, I'm just going to put it on here. Y equals 2 times 3 to the x. I know it's going to cross right there. And all I'm doing is generating this point. When x is 0, 3 to the 0 is 1, so it's 1 times 2. And then if you want other values, okay, we can find them. Now the first, so I'm going to go second table here so you can see them. So 0 goes through 2, 1 goes through 6, 2, 3, 4, 5, 6, so right about there. Let's look at some of these negative values. Negative is 0.6, negative 1 is right about there. Oops. Negative 2 is 0.2, negative 3 is 0.07. What you'll see is it never gets down to 0. These numbers, like that one, 1e negative 4 is 0.0001. And so this is called an asymptote. It's a line you get infinitely close to. And so in this case, the asymptote would actually be the x-axis, because you're getting close to it but never touching it. That's how you spell asymptote. And that's a line you get really close to but don't touch. So we got our y-intercept key point. Let's see here. 41, the polynomial equation with rational coefficients has solutions at, so here we go. Then what other solutions does it have? Well, remember these rational numbers, like 2 minus 3 root 5, irrational, they always have partners. They're conjugate partners. So there's another solution. And the 4 plus 8i, that's an imaginary number. They always come in partners. So 4 minus 8i, conjugate partners. 42 through 45 are about the graph of the function p of x, which is rational coefficients, 5th degree polynomial. So let's just remember it's a 5th degree polynomial. At most, how many imaginary solutions does it have? So we know it's got 5 total solutions because it's 5th degree. Let's see here. We can see it's got 1. This has got to be multiplicity of at least 2. So at most, since that counts at 3 solutions, it's going to have 2 imaginary at most. Now I say at most because maybe this multiplicity at 2 is like a multiplicity of 4 or something like that. We know it has multiplicity, but we're not sure how many. Okay, it does look like just 2 though. If it had 4, it'd be a little bit flatter. Identify the local maximums and minimums. So local maximums right here and right there. So if I'm going to label those or name those, I got negative 2.095. See, maximum, local maximum. And we just have to write down those two numbers. Negative 2.09. I'm just going to put negative 2 and 181. Approximately negative 2 and 181. Okay, you'll give the real numbers. It's just hard here on my screen here. Here's the other local maximum, 2, 100. Okay, so those are local maximums. And let's see, they also want local minimum. So we have one local minimum right there. And, oh, we have more than that. Also right here's a local minimum because it goes higher up here. So this would be a local minimum as well. So we got 2 of them, one at the 0.095, 47.622, and the other one at 40. Okay. So local mins, I'll put the 40, and the other one about 0.0, let's call it 0.1 and 48. Again, put down the real numbers when you're doing it on your test. Describe with inequalities the x values for which it is increasing and decreasing. So I'm going to erase this So we talk about increasing and decreasing. So here it's increasing, going uphill. Then it starts to decrease. Then it turns around, starting to increase. And it's decreasing. Always reading from left to right. And then it increases. So our increases are in green. Let's see, where's it increasing, decreasing? So I'm going to put them right underneath here so you can see them. Okay, now the key values we want to focus off here are the actual x values where these things occur. So there's an increasing region, and it occurs between, looks like -3 and 1. So increasing when x is, well, it's actually increasing before -3 as well. So it's increasing when x is less than 1. Because even before that -3, it'll still be coming uphill. So it's increasing until it gets to negative, I don't know why I said -1, that's -1, 2. Increasing until it gets to -2. Then it starts to decrease. And so it decreases between x is 2 and x is 0, right there. -2 and 0. That should be -2. Then it starts to increase again. It increases from x is 0 to x is 2. Then it starts to decrease again. It decreases from 2 to x is 4 right there. Then it turns around and increases again when x is greater than 4. So we got 3 regions of increasing, 2 regions of decreasing. Describe the x values for which it is positive. When's it greater than 0? Well, if you notice, it's kind of a trick question. Here's the x-axis. And so it's always positive. Okay, when it's x is greater than this -3, it's always above board. Now, right there, it's 0, so we got to check our question. But as long as this x is bigger than -3, we're going to be above the x-axis. So it just says greater than 0. So we're going to say when x is greater than -3, but we have to throw out when x is 4. So we're going to say x is not equal 4. So it's all x values greater than -3 except for the 4. Now, that's not really the right way to write it. Actually, that works pretty decent. I would accept that on a test. Describe which inequalities x values which p of x is greater than 100. So here's the 100 mark right here. When's it greater than 100? Well, for these x values in that region. Let's see here, and then right out here, so from these x values. Now, we'd have to approximate these, okay? And so that's kind of a disingenuous question, but hopefully you'd understand the fact that it's greater than 100 just in this region right up here. Okay, so you'd have to know these x values, which you'd be given on a test. And it's bigger than 100 right here, and so that's, I don't know, 4.8 or something like that. But that'd be that region. It is multiple choice, the test will be, and so you'll be able to pick those out of the lineup and say, hey, it's these values. I think that's everything. So that's a pretty good review of what the test looks like. I know I ran through it quick, but you can handle it.